హలో లైవ్ లో ఉన్నాను. స్టార్ట్ చేస్తుందండి. ఓకే రైట్, థ్యాంక్ యూ. Good morning everybody. Today we are going to discuss the compaction of soils. In the last class we have seen the various discussions regarding the several topics up to the seepage theory, seepage numerical problems, and the problems appeared in previous GATE examination covered in earlier class. And today we are going to take up compaction of soil. First we'll go to complete theory, then some numerical problems, and later the questions that appeared in several GATE examinations. Now let us see the compaction of soil. Compaction of soil means reducing the volume of the soil by the expulsion of the air. Reducing the volume of the soil by means of the expulsion of air. It is done by means of the mechanical methods. And several mechanical methods are to be employed for reducing the volume by making soil particles very close to each other. When soil particles are close to each other, then compaction takes place. And in this process, out of the three constituents present in the soil solids, water and air, only air is expelled from the soil. Part of the air is expelled, and it can be any extent. Total air can also be extended. So in such a case, 0% air voids or a total compaction, 100% compaction is achieved. So that means compaction is the process of reducing the volume of the soil mass by means of expulsion of air by several mechanical methods. And by doing so, compaction is doing so, it increases all the engineering properties of the soil, and hence strength property and all other related properties will improve. And you can look at the diagram, first one, loose soil. It consists of soil solids, water and also air in between. And in the case of compacted soil, next one, all the soil particles are closely intact, and air expelled from the original loose soil, and it is compaction to certain extent. Compaction range can be 0 to 100%. But here, when the soil is completely loose in state, we can say that compaction or relative compaction is 0. When entire voids are expelled from the soil, then that is called the 100% compaction. And you can look at the three-phase diagrams already discussed in the first chapter. The soil mass consists of soil grains, water, blue color, and also air, white spaces. It can be represented in a three-phase diagram: soil, water and air. In the process of compaction, the quantity of soil will be as it is. There is no change in volume of the soil solids, or there is no change in weight of soil solids, and there is no change in volume of water or weight of water in the soil mass. Only air will reduce. Volume of the air reduced in the process of the compaction. So here you can look at air is a certain height, and after compaction, the total volume of the soil mass also reduced. That is by means of the reduction of air. reduction of the air. There is no change in soil grains. There is no change in water content. Only thing during the process of compaction, volume of the air decreases. Volume of the air decreases. So depending upon the amount of air decreases, it may be varying 0 to 100% of the compaction. If the entire air is expelled from the soil, then that is called the 100% compaction or zero air voids. So in the process of compaction, the degree of compaction completely depends on the various parameters: moisture content, the amount of compactive effort or energy expended, nature of the soil, whether the soil is fine grained or coarse grained, and how much mechanical effort is being put onto the soil, and what is the moisture content in the soil. So these are the various factors that depend on compaction of the soil. And compaction increases naturally, density increases, shear strength increases, bearing capacity increases, and stability of slope increases. So that means all favorable engineering parameters increases during the process of the compaction by the compaction process. And compaction decreases settlement. Once the soil gets compacted, further settlement is less. So decreases settlement. And when soil is compacted, voids for flow of water also reduced. So permeability reduced, void ratio reduced, and compressibility of soil also reduced. So all engineering properties improves by means of compaction of soil. And initially, you need to understand the difference between the compaction and consolidation. Consolidation is the next chapter, and tomorrow we are going to discuss on the consolidation chapter. But anyway, in both the methods, the major purpose is to reduce the volume or to increase the density of the soil. For increasing the density of the soil, there are two different means. One is compaction, another one is consolidation. Now let us have a look the total basic differences between compaction and consolidation. In case of compaction, the basic principle here is expulsion of pore air. Whatever the air that is accumulated in the pores, that will be expelled by means of the compaction. Whereas in case of consolidation, expulsion of pore water. Excess water, excess water expelled from the soil mass, then that process is called the consolidation. And in case of compaction, soil involved is partially saturated. Sometimes it may be partially saturated, even dry in condition, and the degree of saturation is always less than 1, because some amount of air present in case of compaction. Whereas consolidation will be taking place only for the fully saturated soil. For fully saturated soil, there is no air present in the soil sample, and reduction of the volume takes place only by means of the expulsion of the excess pore water. And in compaction, it applies to cohesive as well as non-cohesive, cohesionless soils, cohesive soils and also non-cohesive soils. That means all types of soils, compaction can be done. Whereas in case of consolidation, it is only for the cohesive soils, that particularly clay. For particularly clay, the consolidation takes place. And in case of compaction, mechanical means or artificial or human agency is used for giving the energy to the soil. So energy to soil is by means of artificial mechanical means or by means of human means. Whereas in case of consolidation, the application of the load is or otherwise by means of the natural agencies. That means soil below the construction of the buildings may gets consolidated. So that means the load there is the weight of the total building. And sometimes natural agencies. Natural agencies means the overburden pressure over the existing soil. 5. Dynamic loading is adopted because already I told you mechanical means of energy importing is used in case of compaction. So the load is dynamic. In case of consolidation, the static loads. If the building is constructed, if any structure is constructed on the above the clay layer, the load acting on the clay layer is always static. Or any overburden over the clay, it is also static in condition. And in compaction, improves bearing capacity and settlement characteristics. And it is also same in case of consolidation also. Improves both bearing capacity and also reduction of the settlement characteristics on compaction or otherwise after consolidation of the soil. And in case of compaction, it is relatively quick process because we are applying mechanical means of importing energy. It is a quick process. And whereas the structures constructed on the soil or clay is static in nature and it will be very slow process. It takes years together for consolidation of clay layer. And relatively complex phenomena in case of compaction because expulsion, compression and dissolution of air takes place. Whereas in case of consolidation, it is a very simple phenomena of expulsion of water. And compaction is useful for primarily in all embankments, earthen dams, for all construction works which are required to do very quickly. Compaction is always preferable. Whereas in case of consolidation, it is useful for improving the properties of the foundation soil. So these are the basic differences between consolidation and compaction of the soils. And in both the process, the ultimate aim is to reduce the volume of the soil mass. Accordingly, permeability decreases, wide ratio decreases, compressibility also decreases, and all strength parameters increases. Now, compaction theory. Already in the first class, you have seen a relation between bulk unit weight of soil, dry density of the soil, and water content. Gamma equal to gamma D into 1 plus W. So this is the relation. So for any amount of water content W, any amount of water content W, the associated density is bulk unit weight. And from knowing the water content in the soil and its bulk unit weight, we can find out the dry unit weight of the soil, gamma D equal to gamma by 1 plus W. Gamma by 1 plus gamma D equal to gamma by 1 plus W. Okay, so here this is the equation that will be applied for the compacting the soils. Now let us have a look on the graph. So it is a graph drawn between dry density versus water content. Water content is on the x-axis, dry density is on the y-axis. And as the water increases initially at the bottom of the curve, initially the water content in the soil is very low. And as the water content increases, the dry density also increases and reaches to the maximum level. And any additional excess water, again, if by adding excess water, the density is going to decrease and it will be some other value. So why it is going to happen? Initially, when the soil is in almost dry condition or with a small quantity of water, so with the small quantity of water, the repulsion takes place between the soil particles. All the particles are loose in condition. Because there is no formation of the film around the soil particles. There is no formation of film around the soil particles, and all particles are loose in condition. So voids are filled with the air. Once the voids are filled with the air, naturally the dry density of the soil is very low, and this is the initial stage. And afterwards, as the water content increases, that water will form a film around each and every particle, and because of the surface tension, the particles are close to each other. The soil grains are close to each other. Whenever the soil particles are close to each other, the air is expelled, and the density will be more. And this, what is going to happen between the particles because of the formation of the layer around each and every particle? Lubrication increases. As the lubrication increases around the soil grains, the grains are very close to each other because of the surface tension, and that lubrication is maximum at a point where the moisture content is optimum. At the point where the optimum moisture content is optimum. So at this stage, the lubrication is maximum, and close contact of the soil grains takes place, and accordingly the density at that level will be maximum density. If I draw a horizontal line here, the density corresponding to that will be maximum dry density. And afterwards, any further additional water content, any further additional water content is going to have, what is going to happen? Any other additional water content it will fill the voids in the soils. So lubrication effect is maximum at a particular level. After that, any excess amount present, that will be filled in the voids. So whenever the water filled in the voids, then some volume occupied by the water, and naturally the density decreases. As the more and more voids are occupied by the water, as more and more voids are occupied by the water, the density of the soil is going to decrease and reaches to some other value. So this is the basic phenomena, how the dry density increases from initial state to the maximum, and then it decreases. So initially the lubrication effect is more, and formation of the film around the soil particles will always keep the particles intact, and that intact of particles is maximum at the point where the water content is optimum moisture content. And thereafter, the water additional the thereafter whatever the water that is available, that water is filled in the voids, and as the water content is more and more, the water is going to be filled with the voids, and the quantity of water in the soil will be more and more, and hence the density of the soil is going to decrease. Density of the soil is going to decrease. So this is the basic phenomena theory regarding the compaction of the soil. So we can call it as initial stage, addition of water to initial dry soil. Then we can call it as a peak stage, and then you can look at beyond peak. Beyond peak, the water beyond a certain stage, water does not act as a lubricant. It occupies the void spaces between the solid grains, and hence, as the water content increases, dry density of the soil decreases. And there are two terminology associated from this diagram, and these two are important. At the point where the curve reaches the peak value, the density is called the MDD, maximum dry density. and the point at which where the peak occurs, the associated water content is called the optimum moisture content. Optimum moisture content and maximum dry density, these are the two words associated with the compaction of the soil. So you can look at optimum moisture content is the water content at which the soil attains maximum density. And maximum dry density is the density of the soil corresponding to the optimum moisture content. Effect of compactive effort. Already you know that compaction is done by means of mechanical means or by means of human effort. So energy imported to the soil by some means. So depending upon the energy imported, when the energy imported to the soil is more, the energy imported to soil is more, and naturally the compaction will also be more. So you can look at the different diagrams. First one is bottom of it will be lower compactive effort. So that means the compaction energy imported to the soil is less. Whereas second one is somewhat more energy imported to the soil. Third one is higher compactive effort imported to the soil. So as the energy is more, the dry density, maximum dry density will be more. You can look at the peak of the top curve, the maximum dry density is more. And for the medium compactive effort, the maximum dry density is less. And for lower value of the compactive effort, the maximum value is still less. So that means as the compactive effort is more, the maximum dry density of the soil also increases. Soil increases. And at the same time, for lower compactive effort, more water content is required. If the compactive effort is less, more quantity of water is required for its maximum dry density. So this is optimum moisture content for low compactive effort soil, and it is medium. The third one is higher compactive effort to the soil. So that means the optimum moisture content decreases as the compaction effort increases. So as the energy imported to the soil is more, the optimum moisture content decreases. Similarly, as the energy imported to the soil is more, maximum dry density increases. So here, for any case, once the for a given soil, all these curves are for a given soil. Soil is same. For a soil is same, the energy imported to the soil is different. So when you import more energy, more maximum dry density occurs, and corresponding to OMC less value, low value. So our maximum dry density will occur corresponding to the optimum moisture content. So as the effort of energy onto the soil is increases, maximum dry density increases, and at the same time optimum moisture content decreases. And this is another one, zero air void line or 100% saturation line or theoretical maximum density line. So you know already you have seen this is the compaction curve. So lower one is the compaction curve, and of course another curve is also compaction curve with the different energies imported onto the soil. And already you know that the compaction is achieved by means of the expulsion of air. If 100% of air is expelled, when 100% of air is expelled, and that is called a saturated soil, completely saturated soil. So that means all voids are filled with the water. When all voids are filled with water, that is called zero air voids. Air content will be equal to zero. There is no air in the soil if entire air is expelled from the soil. So that is in the case of fully saturated condition. So this dotted line is the curve between dry density and also the water content, where this is an ideal case. Ideal case of air content is equal to zero. And similarly, other one, 95% saturation. 95% saturation means 5% of the air content. 5% of the air content. 5% of the air content is same as that of 95% of the saturation. You know, air content is AC. Air content is AC. Already you have seen symbols earlier. Air content is AC. Degree of saturation is capital S. AC plus S is equal to 1. That is the relation earlier derived. So S plus AC is equal to 1. So 95 plus 5, it will be equal to 1. So if the degree of saturation changes, accordingly air content also changes. And this is another imaginary straight line at the 95% of the saturation. And here by considering various fundamental equations, like chapter 1, relations of the various soil properties, you will get gamma d equal to 1 minus Na into g gamma w by 1 plus wg. So here in the equation, Na means percent air voids. See, Na is different and AC is different. Air content means AC. Air content plus degree of saturation, air content plus degree of saturation equal to 1. But the formula is not related to water content, density, etc. Not with the AC, but it is related with the Na. Na means percent air voids. Percent air voids. So this is the generalized equation, and everybody knows that gamma d equal to g gamma w by 1 plus E. And for partially saturated soil, E can be substituted as Wg by S. Wg by S. And when it is completely saturated, when S is equal to 1, it is Wg and 1 minus A. So for finding the dry density of the soil in terms of percent air voids, this is an equation. So this is the only equation available in the compaction theory. So remember it, G gamma W by 1 plus Wg into 1 minus Na. So here Na is percent air voids. Okay. So here this is the relation between the saturation level and also air content. And you can also remember that completely saturation means it is zero air voids. Zero air voids in the sense that Na equal to 0. Na equal to 0 and also AC equal to 0 for fully saturated condition. So that's why we can call it as 100% saturation is same as that of zero air voids. But 90% saturation, 5% air voids is not correct. 95% saturation, 5% air voids is not correct. Air voids is different. Air voids means Na. Percent of air voids available in the total sample. So that means 100% saturation, 0% air voids are one and the same. But 95% saturation, 5% air voids are not the same. You can look at here. Zero air void line is used to compare and understand the level of compaction. Okay, you can look at here to clear off your doubt. For S is equal to 100%, gamma D equal to G gamma W by 1 plus WG. Because there S is equal to 100 means, S is equal to 100 means Na equal to 0. Na equal to 0. You can also look at saturation 100% means 0 air voids. So Na equal to 0. So when Na is 0, when Na is 0, you will get gamma D equal to G gamma W by 1 plus Wg. And you can also look at Na equal to 0 means the same formula holds good. So that means 100% of saturation or 0% voids, both are one and the same. But if you look at S is equal to 90%, degree of saturation is 90%. So in the 90% degree of saturation means you can see the formula gamma D. Gamma D equal to G gamma W by 1 plus Wg by S. Now what is S value? 90%. 90% means 0.9. If you use 0.9 in place of S, you will get it as 1.11 because Wg by 0.9, that 0.9 will come into 1.11 Wg. So this is the dry density when S is equal to 90%. For air voids equal to 10%, Na equal to 10%, Na equal to 10%. Substitute the Na 10% in the formula. You can look at here. Na equal to 10%. What is the remaining? 90%. 90% means 0.9. So you will get 0.9 G gamma W 1 plus Wg. Is the two values are same? No. You can look at gamma D can be computed. Gamma D can be computed based on the degree of saturation and water content. This is one formula. And gamma D can also be computed basing on the percent air voids Na. So in the first case, where the degree of saturation 100% and Na 0, both values are one and the same, gamma D. But when S is equal to 90%, gamma D equal to this, and when Na equal to 10%, gamma D equal to this. These two are not equal. When these two are not equal, the degree of 90% saturation is not equal to 10% air voids. 90% saturation is not equal to 10% air voids. Remember this. It's a concept oriented line. 90% saturation is not equal to 10% air voids. Now what is correct? You can see 10% saturation is 0 or otherwise 0 air void line or same, one and the same. 10% air void line, 90%, 10% air void line, 90% saturation line are not identical. You can look at here, gamma D values are not one and the same. But 10% air content, remember air voids is different from air content. A 10% air content line and 90% saturation line are same. 10% air content line and 90% saturation line are one and the same, but 10% air voids, 90% saturation are not the same, are not identical. Now look at the various tests that are to be conducted in the laboratory. So in the laboratory, we have two different types of tests to be conducted for compaction of the soil. One is standard Proctor test, or we can call it as light compaction test. Standard Proctor test or light compaction test. And another one is heavy compaction, or otherwise we can call it as modified Proctor test. So this is called standard Proctor test, whereas heavy compaction is called modified Proctor test. And standard Proctor test has its own properties. It is normally to be conducted for testing the soil samples to be used for highways, embankments, and also canal banks. And for a heavy compaction or otherwise modified Proctor test is used for the materials to be tested for express highways, runways, etc. And here there are so many components associated, and rammer is 26 newtons. Weight of the rammer is 26 newtons, and it is always having falling height of 310 millimeters. So that means a compaction of the soil is to be done by lifting 26 Newton rammer through a falling distance of 310 mm. And number of blows to be used for each layer is 25, and mold capacity 1 liter or 1000 centimeter cube. Number of layers for the test is 3, and diameter of the mold is 100 millimeters. So these are the various properties of the mold, and now how many number of layers to be used are 3, number of blows per layer is 25, and 26 Newton load is falling 310 millimeter distance. So what is the energy imported through one drop of hammer? 26 Newton of load is dropping from a height of 0.31 meter. 310 mm means 0.31 meter. So what is the energy imported onto the soil? For each hammer blow, the energy imported is 26 multiplied by 0.31 Newton meter. That is the energy imported for one blow. Similarly, the various standard specifications for modified Proctor test are rammer weight 49 newtons, falling height 450 millimeters, number of blows 25, mold capacity same 1 liter 1000 cubic meter, number of layers are 5, diameter of the mold 100. So in the case of modified Proctor test, we have to go for 5 layers, and each layer is to be applied 25 number of blows for a hammer of 49 newtons through a distance of 450 millimeters. Now, what is the energy imported onto the soil per blow? Per blow, what is the energy? 49 newtons multiplied by 0.45 Newton meter is the energy imported onto the soil per blow. So these are the general specifications. But normally, sometimes the soil is mixing of several things, and sizes of the particles also different. In such a case, we can use large diameter of the. So here 100 mm mold is being used. 100 mm mold is being used for conducting the experiment. But if the sample is more than 20% passing through 4.75 mm, if the sample passing through 4.75 mm is more than 20%, then we can use higher capacity mold of 2.25 liters. That means 2250 centimeter cube. So for this, the height of the mold is 150 millimeters. When 150 millimeter diameter mold is used, the number of blows in each layer is 56 for standard penetration test, and also for modified standard Proctor test, and also for modified Proctor test. So whenever the size of the mold is increased to 2.25, instead of number of blows per layer 25, now we have to use 56 blows in both the standard penetration test and standard Proctor test, and also modified Proctor test. And compactive energy in case of modified Proctor test is more than that of the standard Proctor test. You know, top one is energy imported, or otherwise you can look at for SPT, for standard Proctor test. For standard Proctor test, energy imported onto the soil is energy imported onto the soil is this 1000 is not required. 26 Newton hammer is moving, is giving a blow at a height of 0.31 meter and three layers, each layer of 25 blows. This 1000 is not required. This 1000 is valid only when it is kept 310 mm. Now 1000 is not required. So it is 605 Newton meter per 1000 centimeter cube. So because the volume of the mold is 1000, volume of the mold is 1000, for 1000 square centimeter cube mold, the energy imported is 605, actually 604.5 or 605 Newton meter per 1000 centimeter cube. Similarly, for modified Proctor test, energy imported is 49 Newton hammer dropped from a height of 450 mm, 0.45 meter, 5 layers, each layer 25 blows. It is 2756 Newton meter per 1000 centimeter cube. The ratio of these two, 2756 by 605, you will get 4.55 times. So that means energy imported in modified Proctor test is 4.55 times that of the 4.55 times that of the energy imported by the standard Proctor test. And already I told you, if the soil retained is more than 20% on 4.75 mm, then mold capacity of 2.25 shall be used and associated number of blows shall be 56 for each standard Proctor test and modified Proctor test. So these are the energies imported by using the standard Proctor test and also modified Proctor test. And now let us see what are the various factors affecting compaction. Various factors affecting compaction. One is water content. Already you have seen the entire theory. As the water content increases, compaction increases, reaches its maximum value and then decreases. Already you have seen the curve. The curve initially increases to the maximum and thereby it is decreases. So water content must be in optimum condition. At the optimum level of water content, the density will be maximum and it is called maximum dry density. Then amount of compaction. So already you have seen the diagram. When compactive effort is more, then compaction increases. Compaction increases means the dry density increases or maximum dry density increases. Compaction increases means maximum dry density increases and OMC decreases. Already you have seen the diagrams associated with this. Then type of soil. So there are two different types of soils normally available: coarse grained soils, which have size more than 75 microns, and that means which have more than 75 microns. That is more than 50% retained on the 75 micron sieve. And another type of soil is more less than 50% of the soil retained on 75 micron sieve. So these are the coarse grained soils and fine grained soils. Coarse grained soil attain higher density and lower OMC, whereas fine grained soils will have more OMC and compared to coarse grained soils. Because in case of fine grained soils, particularly clay, the clay possessing high plasticity and requires more water because surface area of the particles is also more. Because all the particles are very small in nature, the total surface area in a given sample of soil is very high in clay and requires more water for formation of film around each and every particle, and more OMC occurs. So for clay soils, optimum moisture content is always more and density is less when compared to the coarse grained soils. So coarse grained soils have high MDD, low OMC, whereas fine grained soils have low MDD and more OMC. So normally what is going to happen, sometimes the soils may also contain organic matter. When the organic matter present, it absorbs more water. When organic content present, more water absorbed, and naturally the OMC value increases and organic content is having less density, so maximum density also decreases. So when the soil contains organic matter, maximum dry density decreases and OMC increases. So here, no need of by hearting any of the lines. You have to understand each and every statement, and accordingly you have to interpret the various results. Because, for example, you just understood clay. Clay is having very minute particles, and it is having high plasticity. Naturally, it requires more water. When it requires more water means more OMC. And whenever OMC is more, automatically dry density will be less. Maximum dry density is less. So like that you can interpret the various results and understand the total base concept. So already I told you here, depending on the type of soil, the optimum moisture content and also maximum dry density varies. So here several types of soils that you can consider: well-graded loamy sand, well-graded sandy loam, like that several things are there: lean silty clay, loessl silt, heavy clay, poorly graded sand. When clay is heavy, you just remember one thing: when clay is heavy, what is going to happen? Maximum dry density is less and optimum moisture content is very high. You can look at the seventh diagram. This seventh diagram is having peak here, corresponding to the point on the x-axis is the water content, maximum water content. At the same time, the ordinate on the y-axis is less. So that means for heavy clay, optimum moisture content is more and maximum dry density will be less. Whereas first one, well-graded sand, when sand means it is coarse grained soils, and you can look at the curve number one. You can look at the curve number one. This is the compaction curve where the density peak value is maximum and associated line corresponding to the horizontal axis is very less. So that means at a low optimum moisture content, the density will be more. So you can remember, for sand, maximum dry density is more, optimum content is less. And similarly for the seventh one, clay, maximum dry density is, optimum moisture content is more. And in between all other combination of the other soil samples present. And our last one, poorly graded sand. Poorly graded sand means it is always having, say, let us consider uniform sand. Uniform sand means all sizes of the particles are same. When all particles are same, more number of voids present. When more number of voids present, the maximum dry density decreases. Maximum dry density decreases and optimum moisture content little bit more. So it is particularly poor graded sand. Whereas well graded sand is entirely different. In case of well graded sand, the voids present in the soil are very small and density will be the maximum. Whereas in case of poorly graded or uniformly graded soil, the voids are more and hence the density will be less. So like that, with the interpretation only, you need to remember, you need to understand all the parameters without any by hearting. Then method of compaction. So already you have seen method of compaction. Compaction can be done static way So simply by keeping some weight on the soil, and gamma D based on the standard Proctor test, gamma D obtained based on the modified Proctor test. So depending upon the amount of compaction that is imported to the soil, gamma D of static is always more than gamma D. So here for a given soil, it is a reverse, please. Something wrong. I will correct in the material and send later. You know that the dry density is in case of modified Proctor test is more. Dry density in modified Proctor test is more than the dry density in a standard Proctor test than in the static test. Whereas in case of modified Proctor test, since the dry density is more, OMC is less, and OMC for SPT is more. So these symbols are in reverse direction. And remember that modified Proctor test is always have high maximum dry density, and modified Proctor test is always have low optimum moisture content. You can look at here, modified Proctor test, the density will be more. Density for modified Proctor test is more than the density for the standard Proctor test. And similarly, optimum moisture content for modified Proctor test is less than the optimum moisture content for the standard Proctor test. So with this you can also observe. So density of gamma D of the modified Proctor test is more than the gamma of the standard Proctor test. Similarly, optimum moisture content of modified Proctor test is less than the optimum moisture content of standard Proctor test. Then sometimes we can use admixtures in the soil. So sometimes if the soils are problematic in nature, we can use admixtures for improving the properties. Sometimes we can use lime or cement or fly ash. Any other admixture can be used for the problematic soils. So if fly ash is added to clay, maximum dry density increases and OMC decreases. So for any problematic soil, what is going to happen? Maximum dry density is less and OMC is more. By the addition of fly ash, density increases and OMC decreases. Next, placement water content. Placement water content means you know that you can look at here placement of the water content. So this is the experiment done in the laboratory. And accordingly a curve is plotted between dry density and water content. But this is the maximum dry density gamma D maximum, and the same value should occur in the field. So in the laboratory, we are using all standard conditions and we got maximum dry density certain value. So in the field, so many variables present, and accordingly, whatever the maximum dry density occurs in the laboratory may not occur in the field. And at the same time, whatever the water content observed in the laboratory is OMC, and in the field we cannot keep exact amount of OMC for compaction in the field. The OMC may be slightly less than the OMC, or OMC in the field may be slightly more than that. So because in the site the soil may have certain amount of soil, and even from soil lump to soil lump also varying some amount of moisture content, and by adding some amount of water, distribution of water to the soil is also not uniform. So that's why sometimes the soil may be having water content, though we are going to, our aim is to keep OMC, though our aim is to keep OMC in the field soil, that OMC may be slightly less than that, or it may be slightly more than that. If the OMC in the field is slightly less than that, it is called a dry side, because this is the maximum optimum value. The left of the optimum value is called the dry side of OMC. Dry side of OMC. Sometimes water content may be slightly more than OMC. Slightly more than OMC. Then that case is called the water content on wet side of OMC. On wet side of OMC. So depending upon the water content on left side of OMC or right side of OMC, certain properties will improve, and accordingly we use optimum moisture content in the field. So placement of water content. The soil compacted on wet side of OMC, that means on the right side of the OMC, to avoid large expansion and swelling pressures. So in the field, if we provide optimum moisture content more than the laboratory value, there are some advantages. Large expansion is avoided, expansion of the soil is avoided, and swelling pressures also avoided. So the swelling will be less, and expansion of the soil is also less. So these two can be avoided by providing moisture content in the field slightly more than OMC. So example for it will be core of the earth dam. So that means the central part of the earth dam is called the core of the earth dam, and under pavements, just below the pavements, the soil must be in the wet side or under the floors. So just below the floors, the soil must have wet side of OMC. Wet side of OMC. Because when soil is kept on wet side of OMC in case of core of earth dam, for below the pavements, below the floors, then it always gives a better results. Expansion will be less, and also swelling pressures also less. So particularly core of some sections are like this. Core of earth, the water content required for core of earth dam is equal to exactly OMC, less than OMC, more than OMC, or any other value. Like that the questions may be asked. So here it is wet side means the water content is slightly more than the laboratory OMC. So particularly in case of earth dam, when water is provided on wet side of OMC, the permeability must be low, because the what is the core of the earth dam requirement? Core of the earth dam requirement is it must have low permeability, and it must have very low swellings. Swelling low, permeability low, and for that property is required for the core of earth dam. So the moisture content must be on the wet side of OMC. So similarly, the soil compacted on dry side. Dry side means left of the OMC. Left of the OMC to have higher shear strength. So whenever shear strength requirement is more and compressibility is low, such a cases the water content must be on the dry side of OMC. So examples are outer shells of earth dam. So earth dam is having outer portion, it is called shell, and core of the earth, which is the heart of the earth, which is provided at the middle of the earth. So middle of the earth, must be always on the wet side, whereas outer shell, it must be on the dry side of the OMC, or even highway embankment. So when embankments are provided for highways, the water content must be slightly less than optimum moisture content. What are the requirements for outer shells of earth dam? Outer shells of the earth dam, it must have high strength. High strength means high stability also. So the slope of the earth dam must be stable in condition. So that is possible only when the strength is high or low water poor water pressure or high permeability. So permeability will be high for the outer shell of the earth dam, and for the heart of the earth dam permeability should be very low. Similarly, what are the requirements for highway? Highway strength requirement is one, and compression of the highway also should be very low, because when the compression takes place, it gets damaged. So when these two are the requirements, it must be on the dry side. So now let us have look what are the various things that improve different sites. So effect of compaction. So by using the water content on the dry side, you can look at here. It is not visible. This is property of the soil, and this is dry side of OMC. This is called dry side of OMC, and it is called wet side of OMC. Wet side of OMC. So when the soil gets compacted, when the soil gets compacted, the structure also changes. Soil structure also changes, and that structure, these properties are dry. First, remember, first one is dry, second one is wet. So when the water content is on the left side of OMC, the type of structure of the soil particles is flocculated. Flocculated type of structure will be there. And whereas in case of wet side, if the water content is more, dispersed structure will occur. Dispersed structure will occur. Similarly, water deficiency. Since the water content is less than OMC, water deficiency is high here, whereas other side low. Permeability. Permeability, when it is on the dry side, it is high, the other side low. So you remember all these are one side high, other side low. Similarly, compressibility, at low stress, it is low for dry condition, low and high for the wet condition. And sometimes the structure may be, soil structure may be at high stress. If the stress applied on it will be very high, it will be high, and associated on the wet side will be low. Then swelling. Swelling properties for on wet side is dry side is high, on wet side is low. Shrinkage is low on dry side, wet side will be high. Pore water pressure is low on dry side, wet side high. Undrained strength, that is simply strength, it is high in case of dry soil and low in case of wet soil. Stress behavior. So since the water requirement is less than OMC, it is still in brittle condition, whereas water content is more than OMC. So the soil which is under wet side of OMC is called the ductile. So these are the various associated properties. So according to the type of requirement, for example, we require where the permeability low. For a structure where the permeability low means we always use water content on wet side of the OMC. Wet side of OMC. See, it depends on the requirement. And sometimes if the strength requirement is more, that means the stability of slopes and also angle of shearing resistance, etc. will be more, or bearing capacity, etc. will be more. Then naturally it is high in case of wet dry side. So we have to use water content on dry side of the OMC. So depending upon the requirement for different types of structures, we have to use either water content on the wet side or on the dry side. So remember, these are the very important points. You remember, core of the earth dam is on wet side, under payments, under floors on wet side. Then outer shell of earth dam is on dry side. Highway embankment is on dry side. So these are the very small and important points from the examination point of view. Now, sometimes in the field, what we do, we cannot calculate water content exactly. Normally, in the laboratory, what you do for computing the water content, initially you will take some sample and you will weight it, and it will be kept in oven for 24 hours, and the next day you will get water content. But in the field, we cannot wait for 24 hours for the want of water content purpose. So there is a Proctor needle, or otherwise plasticity needle. This can be used for finding the instant water content by calibration into instant water content, and also the dry density. Dry density. It's simply just remember, it is used for finding the field water content and also dry density by means of the calibration. So what normally we do is, we are going to insert this needle for 7.5 centimeter onto the soil, and you will know the associated penetration resistance, how much resistance will be exerted by penetration of the 7.5 centimeters. So according to the penetration resistance, calibrate it and find out the water content and also dry density of the soil. So this is the equipment used, small equipment used for finding the field requirement of measurement of W and also dry density. So relative compaction. So the next term is relative compaction. Already you have seen one similar type of term. Already you have seen similar type of term earlier in case of first chapter, that is called the relative density. Here it is relative compaction. What is the difference? Is both one and the same or different? Is same one and the same or different? Relative compaction. So already you have seen one term, relative density. Relative density ID will be equal to, what is the formula associated with it? ID will be equal to, what is the formula? ID equal to E maximum minus E divided by E maximum minus E minimum. So this is the formula for computing the ID, relative density. Now it is relative compaction. Is both one and the same or different? In the case of density, what is that you have seen? The soil may be having a wide ratio infinite, and wide ratio will be equal to E minimum, E maximum, and at other point E minimum. So when wide ratio is E minimum, wide ratio is E minimum, what is the dry density? Dry density will be maximum, gamma D maximum. When wide ratio is maximum, dry density will be equal to minimum. Gamma D will be equal to minimum. And what is the value at this point? Gamma D will be equal to 0. So when wide ratio is infinite, the dry unit weight of the soil is 0, because when E is infinite means there is no soil particles, and gamma D will be equal to 0. And E equal to E maximum, the density will be the minimum. And when E will be minimum, density will be the maximum. So that means wide ratio increases from infinite to minimum value. And it may not be 0 always, we can call it as E minimum. And accordingly, you computed the value of ID in earlier case. So now it is relative compaction. So what is the relative compaction? So in this particular case, how the relative density varies? How the relative density varies? You know, relative density ID value varies from 0 to 1. Where the ID value is 0, if you substitute E is equal to E maximum, E is equal to E equal to E maximum, what is going to happen? Here the value will be equal to 0, whereas the value will be equal to 1. So this is called the variation of the relative density. And similarly, if you draw a line with the same properties E equal to infinite, E minimum, etc., at this point, the relative compaction, we can call it as RC, relative compaction is 0 here. Why relative compaction is 0? The density is 0. You know, the relative compaction means density in the field by maximum dry density. So when the density in the field is 0, then RC equal to 0, whereas here at this level RC equal to 1. So you can look at here, the relative density is entirely different from relative compaction. So relative density I varies from 0 to 1. It starts at the value where E is equal to E maximum to E minimum. And whereas RC is starting from RC equal to 0 at the point where the density equal to 0, and it will be maximum equal to 1. So this is the difference between relative density and also relative compaction. Both of these two are not same, but it looks like the same, but it is not the same. And normally 90 to 97% relative compaction can be achieved. For example, in the laboratory, if the density achieved gamma D maximum equal to 20 kilonewton per square meter cube, 20 kilonewton per meter cube. In the field, it must be 0.9 to 0.97 times of 20 kilonewton per meter cube. And particularly for runways, it must be it must achieve 97.5%. No, not even 97. Sometimes for pavement, very high quality pavements and also runways, the degree of compaction must be more than 97.5%. So that means the density to be achieved in the field is 0.975 multiplied by 20. So you can look at the diagram, you can look at the formula. Relative compaction is this compaction is always compared with the theoretical value. Theoretical value means maximum dry density obtained in the laboratory, and the numerator is the dry density in the field. So density of the field divided by maximum dry density is called the relative compaction value, and it is normally 90 to 97%. Sometimes for special cases it may be more than 97.5%. Particularly for runways, the degree of compaction must be more than 97.5%. And you can look at this compaction of sands. So far you have seen the compaction of soil, it is general, but it is sand, compaction of sand. Is it possible to compact the sand? So whenever you try to compact the sand, automatically again it will come. Say for example, if you import energy to the sand in case of Proctor compaction test, and apply the energy, what's going to happen? It compacted and immediately it comes out. It compacts and also it comes out. So when next poking is adjacent to that, already compacted portion will again gets disturbed because there is no cohesion for the this soil. Cohesion for the sand is hello. Is it visible? Screen is visible now. Okay, right. uh, Compaction of sands. So in case of compaction of sands, just you can imagine that while walking on the sand near river, when the sand is completely dry in condition, it is very easy to walk over the complete dry sand because the dry sand is having maximum density. When the sand is having some percentage of moisture and volume will be more, it bulks. So increases, and because of the increase in volume, it's very difficult to walk over the soil with some quantity of water in the sand. And at the same time, near to the water in the river, very close to the water in the river, and because of complete saturation of the sand, it gets fully compacted and it is also very easy to walk. So that means the sand will have maximum density when it is completely dry in condition or when it is completely submerged in condition. When the soil is completely dry, the density will be the maximum. When the soil is completely submerged, the density is also the maximum. And in between, the density varies. And this soil cannot be tested exactly in the laboratory by using a standard Proctor test. So when you apply some blows and soil gets compacted and again gets disturbed, etc., and you may not get exact value. And this is the characteristic of the sand between dry density versus water content. What is going to happen is when the air dry condition, that means there is no moisture in it. When there is no moisture, density is more. And as the moisture is increases, the density will become less. You can see point of minimum density. When the density is minimum means it bulks more, volume will increase. So it is perfectly dry in condition and it is having some moisture where the volume will be more. Hello, presentation రావట్లేదా? Uh, 1 minute. Oh, Krishna, 1 minute. Presentation పోవట్లేదు ఏంటిది ఇవన్నీ ప్రెజెంటేషన్ వాళ్ళకి వెళ్ళలేదు. ప్రెసెంట్ ఇంకోసారి ఇంకేమైనా వస్తున్నా
repeated.
Is it visible now? Hello? Oh, it is visible. Okay, thank you. So you can look at for compaction of sands. In the case of compaction of sands, when the sand is completely air dry in condition, the density will be more and more compacted. And as some percentage of moisture present in the sand, it bulks and volume increases. So naturally the density decreases, and with the increase of certain percentage of water, it reaches to the minimum value. And afterwards, when the water content is more, it is continuously increasing and reach maximum value at R. Here it is 100% saturation. So it is just like 100% saturation means it is just like sand near to the water flow. At the in the river near to the water flow, if you just walk on the sand, it's very comfortable because entire sand is having high density. When the density is more, there is no say settlement. So that's why we feel more comfort while walking near the flow in stream in sand near the flow of water. And similarly, when the soil is slightly wet in condition, when the sand is slightly wet in condition, it bulks, volume is more, and while walking over the some moist soil, it is very difficult to walk. And at the same time, if the soil is completely dry in condition, the density is also relatively more. And here, walking on completely dry sand is also more comfortable. So that means density is more in completely dry sand, or density is more in perfectly saturated sand. So this is regarding the compaction of sands, and it is different with the other types of soils. And at the same time, you can also look at the diagram, percentage bulking versus water content. Is a laboratory experiment already have done. And initially, when the soil is dry, it has some density, and as the water content increases, the volume increases. Whenever volume increases, the density will be decreases, and it volume increases to the maximum extent because all the water particles in this region form a film around each and every particle of sand, and it will give what is called surface tension. And because of that surface tension, each and every particle repulsion takes place. Repulsion between the particles takes place. Because of the repulsion of the water particles, the volume increases up to here. At this point, density will be very low. And again, any additional amount of water content decreases the bulking, because here what is going to happen is the water weight is dominating than the surface tension around the particles. So that's why again the particles are coming close to each other, and maximum density occurs at this point. Maximum density, or otherwise minimum bulking, maximum density or minimum bulking. And particularly in case of pure sand, this is a empty container or beaker, and this is the sand completely poured for a height of V1, volume V1. It is moist sand, and once moist sand, it is large height compared to the other one. And this is the case of sand, the same sand, and completely submerged with water. Completely submerged with water, so that the volume of the sand decreases to V2. Volume decreases to V2. And the cross sectional area is same. So height is H1, Here height is h2. So you can represent buckling everything in terms of the height only. So what is the percentage of buckling for a given soil? V1 minus V2 by V2. So here denominator is V2 only, because V2 is the standard one. Whatever may be the amount of water, it is completely saturated, and V2 is always constant. Whereas V1 is varying depending on the water content in the sandy soils. So this is the buckling, and also the buckling phenomena in case of sands. And buckling is entirely opposite to the density. And this is the generalized curve for compaction of sands. Then in situ compaction. So that is field compaction can be done in several ways. Two different soils are there: granular soils and also cohesive soils. For granular soils or cohesive soils, the compaction in the field can be done only by means of layers. We cannot keep a very large heap and compaction. That compaction may not reach to the bottom level. So in general, for cohesive soils can be done, and the principle involved here is impact principle. So that means for cohesive soils, we are going to give energy by means of the impact principle. Whereas in case of cohesive soils, cohesionless soils, tamping can be done, kneading can be done, and vibratory principle. Cohesionless soils means sandy soils. Sandy soils will be more compacted by means of vibration. By means of vibration. And cohesive soils will be well compacted by means of the impact. By applying a large amount of force onto the soil, that is called the impact principle. And in both of these two cases, there are several varieties of compaction with different equipment. One is rollers, and everybody knows that this is the roller that is to be used for compacting the soil, and particularly this will be used for compacting gravel in waterbound macadam road, WBM road, and it imparts static compaction to the soil. So there is no dynamic. It is just rolling. It is just moving, and where entire weight is placing on the soil mass. So we can call it as only static mass. There is no vibration or there is no impact for transmitting the load onto the soil. Then compression pressure is low because of large contact area. The entire soil is contacted for the entire drum, because the drum is perfectly horizontal in shape, and the stress or pressure acting on the soil will be very low, and it is suitable for compacting granular bases and for highways. And you know that the compaction, how the compaction is to be done, how many times this roller has to move from one place to the other place. So that is exactly equal to the amount of energy amount of energy amount of energy required as per the standard. In the standard Proctor test, we are importing energy as 26 into 0.31 into 3 into 25, that is 604.5 kilonewton meter. That energy is to be imported by means of the roller, and that will be achieved only when 8 passes are required. So when a pavement requires 8 passes, 8 times the roller moves, 8 times roller moves to achieve the equivalent standard Proctor compaction value. This is one type. Then pneumatic tide. Pneumatic tide. So pneumatic tide means the pressure is applied. In previous case, there is no pressure; it is just moving static load. But here dynamic load. So dynamic load is by means of kneading action. So needles will be there at different places. You can also look at needle in between. These needles also will be acting and needing compaction can be taken place. So here the level of the ground is uneven. Though the level of the ground is uneven, by means of pneumatic tied rollers, this entire soil will be compacted to the same level. Entire soil will be compacted to the same level by means of the kneading action. And a wobble will there. So here pressure also uneven. So wherever more undulations are there, more pressure will be applied onto it. Wherever undulations are less pressure will be applied onto the soil, and ultimately the compaction of the soil is uniform whether the soil is having undulations or not. So it is most suitable for wet cohesive soils. But it can be useful for cohesive and also non-cohesive soils, most appropriate for the wet cohesive soils. So in the examination, the questions are like this. The most appropriate soil to be compacted by using pneumatic tied rollers is like that questions will be there. Then sheep foot roller. Sheep foot roller. So here the meaning is sheep foot. You can look at here, all these are the sheep foots. The shape of all these projections are like sheep foot. So that the roller is called the sheep foot roller. And it is in this particular case, the stress intensity on the soil is very high because the load transferred to the soil only through the base area of the foots, only through the base area of the foots. So that's why the pressure exerted on the soil will be very high. So it is used for compacting the core earth of the dam. So at the central part of the earth dam, where the more compaction is required and permeability almost to be zero, in such cases it will be sheep foot rollers are to be used. And sometimes this equipment is arranged with tamping and also kneading. Kneading means needles that are pushing onto the soil, and it is most suitable for the clay soils. The question may be here, sheep foot rollers are used for compacting sandy soil, gravel soil, clay soil, silty soil, etc. Answers may be there, and clay soils, it is used for best compaction, sheep foot roller. Okay. And whereas in case of granular soil, if granular soils are used, but for example, sandy soils, when you use sandy soils, what is going to happen? These foots will press, and again the sand will be taken out. You can see, observe it. It is not suitable for granular soils, as the sand tends to loosen these continuously, because these sheep foot pushing and again it is pulling. By pulling, the sand gets loosened, and it is not at all suitable for granular soils. It is only for the cohesive soils. Then grid type of rollers. Then you can look at here grid type of rollers. So all these are that means the pressure applied onto the soil is by means of small projections formed in the shape of the grid. So it is suitable for all types of soils, including wet clays and silts, but not for the sandy soils. But not for the sandy soils. Next one. Sometimes we can use rammers. So rammers are for local small areas. Compaction can be done. It can be dropping type or pneumatic type, or we can call it as internal commission type. We can just look at for small areas to be compacted. This dropping type of hammers are to be used, and it is used for cohesionless soils. And normally it is used for all sort of small confined areas. Compaction can be done all confined areas. That means beds of drainage trenches. A small trench is to be taken up, and for compaction of the soil within it, this dropping type of hammer is used, or backfills of bridge abutment, etc., or otherwise pneumatic equipment can be used. So here pressure is applied pneumatically, and pneumatic type of rammers are also can be used for compaction. Then tampers. So manual compaction using tampers, sometimes it can be attached with the mechanical arrangement also. And where the areas are small, trenches or behind retaining walls, or otherwise within the scope of a small construction of the building, the soil can be compacted by means of tampers or also small rammers. Then vibrators. Vibrators will be used only for the sandy soils. It is most important point. Sandy soils can be compacted by means of vibrators. And here several things are there: vibrating drums, and vibratory pneumatic type, vibrating plate, vibro float, all vibro. So that means any equipment that is giving vibrations, that can be used for the compacting sandy soils. Particularly this vibro float, it is normally what is going to happen is the compaction is to be done first from the bottom of the soil and then to the top. It is vibro flotation means a method suitable for compacting thick deposits of loose sandy soil, and flotation method is first compacts a deep zone. So at the bottom of the zone, soil zone, it will be compacted first, and then it works towards the top. So these are the various methods that are used for the compaction. With this, the entire theory is over. Now let us have 15 to 20 minutes of numerical questions in compaction method. Now let us see the first problem. These are not the gate questions. These are the generalized questions, and after completion of these questions, then we move to the gate oriented previous questions. Next, an embankment is to be constructed by compacting layers of 300 mm thick. So that means the embankment will be raised at each and every time by keeping the soil 300 millimeter thick. The rammer used for compaction has foot area 0.04 meter square. So we use rammer, and that rammer has a base area 0.04 square meter. The energy induced per drop hammer 500 Newton millimeter. So at one compaction, one time drop of hammer, this much energy is imported onto the soil. Assuming 50% more energy in each pass over compacted area due to overlap. That means what is going to happen? We are going to compact the soil by means of several layers of 300 mm thick. So first we compact first 300 mm, then second 300 mm. While compacting the second 300 mm, the impact will be there on the first 300 mm also. So that's why 50% more energy in each pass is required because of the overlap of the different layers. So for this situation, the number of passes required to develop compactive energy as per IS light compaction is. That means by doing so, the total energy imported onto the soil is as per the light compaction, or otherwise as per the standard Proctor test, as per the standard Proctor test. So you know that energy imported as per standard Proctor test is 26 newtons of rammer is falling through a height of 31 centimeter, falling through a height of 31 centimeter, that is 0.31 meter. Three layers are to be used. Each layer 25 blows, 604.5 Newton meters per meter cube. For 1 meter cubed of for 1 meter cubed of concrete soil, we are going to use 604.5 Newton meter of energy. The same energy is to be imported on it. But here what is going to happen? Each drop is 500 Newton millimeter is imported. Each drop is 500 Newton is imported. So energy imported on soil layers 500 into 10 minus 3 because is converted into meters. This is the energy divided by volume because this is per unit volume meter cube. So the force is applied in a foot area of 0.04 meter square, foot area of 0.04 meter square, and that is having thickness of the layer 0.3. So the volume of the soil taking the impact is 0.04 into 0.3. So you will get 41.67 Newton meter per meter cube. So that means this is for one pass, this is the energy imported onto the soil. Energy imported onto the soil. But what is the energy requirement? Energy requirement is 604.5. 604.5 and for each pass energy must be 50% more. Energy must be 50% more due to overlapping. So now you can use here 50% energy more means 1.5 multiplied by energy for one pass 41.67. You can see 41.67 and n number of passes required are n, which must be equal to energy as per the IS light compaction. As per IS light compaction already computed 604.5 and this is the standard energy as per light compaction and this is the total energy imported onto the soil which is equal to standard Proctor test. So basing on that n is equal to 9.6. So 10 passes are required to achieve the standard Proctor energy in the field. So this is the base requirement. Here there is no formula, nothing. Only understanding the question is more important and accordingly work out the parameters. Now let us see the second one. Void ratio of granular soil deposit. Void ratio of void ratio of, can look at, is it visible now? Arrow mark is visible. A void ratio of granular soil deposit is 0.6. So that is E is equal to 0.6. The maximum and minimum void ratio of the soil were found to be 0.8 and 0.4 respectively. You know, E maximum 0.8, E minimum 0.4 and natural void ratio 0.6. The relative density and relative compaction respectively are. You know the relative density means already you know the formula ID equal to E max minus E by E max minus E minimum. You will get it is 50%. Relative density. What is relative compaction? Relative compaction is nothing but dry density in the field divided by maximum dry density. Dry density in the field by maximum dry density. So when you will get maximum dry density or what is the formula for dry density, you can look at here. Gamma D equal to G gamma W by 1 plus E. And you know G is soil grain specific gravity which is constant. Gamma W for a given water, gamma W also constant. So dry density is inversely proportional to 1 plus E. Dry density is inversely proportional to 1 plus E. So that means as the voids are more, density is less. Density is less. And so now look at here, gamma D field. Gamma D field. What is the gamma D field? Gamma D field is associated with the void ratio of 0.6. because 0.6 wide ratio is the wide ratio of the granular deposit. So this is 0.6 is the field. So what you do, gamma D field means it is proportional to 1 by 1 plus E. So you can look at 1 by 1 plus 0.6. And gamma D maximum. Where do you get gamma D maximum? You will get gamma D maximum when the wide ratio is minimum. When the wide ratio is minimum, gamma D will be the maximum. So what is gamma D maximum? It is 1 by 1 plus zero point 0.4 and multiplied by 100 you will get 86%. So already I told you relative density is not same as relative compaction. So in this problem relative compaction is 86%. So here this formula is known to everybody and it is easy to understand the concept involved in computing the relative compaction of the soil. Next one. An embankment is to be constructed from the borrow pit with properties. So these are the properties of the borrow pit. Embankment is to be constructed from the borrow pit with properties C equal to 0.8, water content 0.15 and 2.66 and 2.66. So these are the embankment is to be constructed by taking the soil sample from the borrow pit, and the borrow pit is having properties of 0.8 to 15% and also 2.66. The compacted volume of the embankment is 1000 meter cube. So embankment is to be constructed for a volume of 1000 meter cube and its unit weight is 20 kilonewton per meter cubed, yet its water content 20%. So volume of the embankment 1000 meter cube, density of the embankment 20 kilonewton per meter cube, then water content in the embankment is 20%. So these are the three properties of the embankment. A truck of 10 cubic meter is used to transport the soil from borrow pit during excavation and dumping of soil in a truck. The soil increases in volume by 10%. What is going to happen? Initially, we keep soil in the truck for a volume V. And while moving and during transportation, the soil gets loosened and volume increased by 10%. The number of trucks required for transporting the soil are. How many number of trucks are required for transporting 1000 meter cubed of the soil? That is the question here. So now there are several different methods. Now let us look at a simple and direct method that you know. Okay, let us look at here for embankment. Already you know the embankment unit weight is 20 kilonewton per meter cube. Embankment is having water content of 20%. So gamma is known, W is known. You can find out dry density of the embankment. Dry density of the embankment is gamma by 1 plus W. So you will get 16.67 kilonewton per meter cube. So once the dry density is known, the gamma D equal to G gamma W by 1 plus E. In this equation, only E is the unknown value. Compute the E value. So in the first chapter of the relations, you have established a relation volume 2 by volume 1 equal to 1 plus E1 by 1 plus U2. So you established earlier this equation. The same equation is being used now for computing the volume of the soils. Already you know for embankment 1000 meter cube of volume and its wide ratio 0.596 just computed based on the given data, and V2 means what is the volume of the what is the volume of the soil excavated from the pit? That is V2. What is the volume of the soil excavated from pit V2? Its associated void ratio 0.8. It is given in the problem. Associated V2 is 0.8. So from this equation, if you substitute, you will get V2 equal to 1127.8 meter cube. So that means even 1127.8 cubic meter is excavated from the borrow pit, that is equivalent to 1000 meter cubed of soil in the embankment. Hope you understood. When 1127.8 cubic meter is excavated, that is equal to 1000 meter cubed of soil in embankment. But during transportation, what is going to happen? It gets loosened. During a transportation, it gets loosened. So that is volume increases by 10%. So allowance of 10% during transportation. So what is the volume now? 1.1 into 1127.8 is 1240.6. So this is the total volume. And the number of trucks required will be volume by volume of the truck. Volume of each truck will be 10 cubic meters. So 124 trucks are required. So 125 trucks are required now to transport the soil from borrow pit to the embankment. This is the first question. So coming to the back, the second question. The quantity of water to be applied for embankment to achieve desired water content is. What is going to happen in the borrow pit? In the borrow pit, the water content is only 15%. Water content is 15%. And this 15% water content is soil is taken to the embankment, and at the embankment the water content must be 20%. So that means there is some improvement in water. So we need to apply some water for the embankment to achieve the desired water content. So the question is, how much quantity of water is to be applied? How much quantity of water is to be applied from 15% to 20%? That is the question. So for that, Ws equal to W by 1 plus W. So this relation also seen in the first chapter. Weight of the soil solids equal to total weight by 1 plus W. Total weight by 1 plus W. So from also, water content, the small w equal to weight of water by weight of solids. So weight of water can be written as small water content into Ws. This Ws is W by 1 plus W, and substitute that here, small w, W by 1 plus W, and substitute it, you will get 833.33 meter cubed of water is required. So this much water is added to the embankment, then the water content in the embankment is 20%. 20%. So here in the same problem, some other method also given that you can look at later how it will be. I will switch over to the next problem, and I leave it some of the problems which are common base concept. Now let us see one more problem, and this is the last problem probably. An embankment for a highway of 24-meter wide, 1 meter thick is to be constructed from a sandy soil trucked from a borrow pit. So soil is taken from borrow pit, and it is to be constructed for a 24-meter wide and 1 meter thick soil. The water content and void ratio of borrow pit are 12% and 0.7 respectively. Length of the road is 1 kilometer, G for soil 2.7. Several questions may be asked. In the examination, only one question will be asked. Here the question is the dry unit weight of sandy soil from borrow pit is. What is dry unit weight? G gamma W by 1 plus E. Knowing all the values, you can get the thing. It is a very simple one. Second question. The number of 10 cubic meter truckloads of sandy soils required to construct embankments are. So how many trucks are required here? What is the volume of the soil? Volume of the soil is 24 meters wide, 1 meter thick, and 1 kilometer length. 1 kilometer length. So volume is 24 into 1 into 1 kilometer, 1000 meter. So 24,000 meter cubed of soil is required. So number of trucks required will be by 10, 2400 trucks, because here there is no loss of soil, increase of volume of soil, decrease of volume, nothing is mentioned here. You can find out total volume by volume of each truck. Then third question, weight of water transported, weight of water transport per truckload. So in each truckload, how much water content available in the soil? So gamma D equal to Ws by V, you know, gamma dry density equal to Ws by V. Ws or WD both are one and the same. So gamma D multiplied by V, already you know gamma D 15.88 uh, into Ws by volume. So that volume will be 10 because each truck 10 meter cubed is there. So 158.8 kilonewton is the dry weight. When once the dry weight is known or solids weights is known, weight of water equal to water content multiplied by dry weight, you will get the weight of water. You know, 12% of water content in the borrow pit. You can see the question, 12% in the 12% of water content in the borrow pit. So use 0.12 into that. So these are the different types of problems that are associated with the compaction of soil. Now let us move to some previous gate questions. So here it's a direct question. Nothing is there. All parameters are given. Which formula is correct? So you know already gamma D equal to G gamma W by 1 plus GW. 1 plus E, in place of E, S is equal to 1, so GW. So identifying the simple formula in it. Next question. OMC SP, MDD SP. Denote OMC means optimum moisture content and maximum dry density obtained from standard Proctor compaction test. So here it is given OMC means optimum moisture content, SP means standard Proctor test. So OMC in standard Proctor, MDD in standard Proctor. Then OMC MP and OMC MP, MDD MP denote the what are these two? Optimum moisture content in modified Proctor test, maximum dry density in modified Proctor test, denote the given. Okay, which one of the following is correct? What is correct? You know that in modified Proctor test, more compactive effort imported and maximum dry density in modified is more than the Proctor. Similarly, water content in modified is less than the water content in standard Proctor test. So it's only original thing. You can look at B. Optimum moisture content in standard Proctor is more than optimum moisture content of modified Proctor, and maximum dry density of standard Proctor is less than maximum dry density of modified Proctor. So once you understood the basic theory, you can answer the questions. But here these symbols are given to understand the question. These are not the symbols. To only thing is question can be framed in any way, and understanding the question is important. Once you understood the question clearly, and accordingly you can answer the question. Third one, an embankment is to be constructed with compacted cohesion-less soil. Cohesion-less soil. The volume of the embankment is 5000 meter cube, and target dry unit weight is 16.2 kilonewton per meter cube. So embankment volume is 5000, and it has to compacted by getting unit weight is 16.2 kilonewton per meter cube. Three nearby sites, see figure, have been identified from where the required soil can be transported to the construction site. So there are three different sites. So this is the construction site embankment. Site X is available soil with a wide ratio of 0.6 and 140-kilometer distance. Site Y, wide ratio is 0.7, it is 80-kilometer distance. Site Z, 0.64, 100 kilometers distance. So three possible sites are available for construction of the embankment. The wide ratios of the different sites are shown in the figure. Assume the specific gravity of soil 2.7 for all these sites. If the cost of transportation per kilometer, if the cost of transportation per kilometer is twice the cost of excavation per meter cube of borrow pits, which site would be most economical solution? So here, what are the cost of excavation at the site is one important thing. Another one is three different sites are at three distances. So cost of transportation also associated with. So cost of the material is nothing but cost of excavation plus cost of transportation. So which site gives optimum economical solution? Which one gives optimum economical solution? It's not a really a question, it is a generalized question that you can answer. Okay, either site X, site Y, site Z or any of the sites. You can look at volume of embankment 5000 meter cube, unit density is 16.2. And you know that V by 1 plus E, V by V1 by V2 equal to 1 plus E1 by 1 plus E2 formula, you know. So what you do is, it is for embankment, V by 1 plus E, and it is X site, Y site, Z site. X site, Y site, Z site. And you know, gamma D equal to this, and accordingly E. So this is the E value for the embankment. E value for the embankment. So E value for embankment is known, and V 5000 for embankment is known, EX is known, EY is known, EZ is known. So accordingly, find out volume of the X material, volume of Y material, volume of Z material. So volume of X material is this, volume of Y and volume of Z. So these are the three. That means if the volume of X material of 4854.4 is taken, and it can be constructed the embankment. Or if the soil is from Z, 5158 cubic meter is required for the same construction. So what is the economy here given? Let us assume that cost of excavation of 1 cubic meter of borrow pit is C. Cost of excavation, anywhere excavation is say 1 cubic meter is C. And what is cost of transportation of 1 cubic meter per kilometer to C? Already in the question it is given. I'll show you again. If the cost of transportation per kilometer is twice the cost of excavation per cubic meter of borrow pit. So that is given. So cost of transportation of 1 cubic meter is 2C. So for the cost of X site is Cx is C multiplied by 4854. 4854 cubic meter is to be excavated, multiplied by C, and distance, X distance is 140 kilometers. So 140 kilometers multiplied by 2C, and you will get this. Like that for Y, for Z. So out of all these, which one is lowest? The lowest is 5134.4 C. So that means the cost of excavation from site X and transported and constructing the embankment is cheaper out of all the three available places X, Y, Z. So answer is X is more economical. X is more economical. Okay, it's a theoretical question that you can look at. The following statements are made on compacted soils where DS stands for the soil compacted on dry side. DS means soil compacted on dry side of optimum. WS stands for soil compacted on wet side of optimum. Identify the incorrect statement, not correct statement. Identify the wrong statement. You can see soil structure is flocculated on DS. Already some table explained earlier. In a dry side of OMC, the soil is in flocculated shape, whereas on wet side the particles all are dispersed. So this statement is correct. Consection of pore water pressure is low on dry side and high on wet side. You just look at the table given in the theory and accordingly you can answer it. On drying, shrinkage is high on DS and low on WS. No, shrinkage in dry side is low. Since it is low, so this is not correct option. C is wrong option and it is to be answered. On access to water, swelling is high in dry side. You can see swelling is high in dry side. So for answering this question, you need to understand what is optimum content, moisture content, what is dry side of OMC, wet side of OMC, and how the properties will change from one side to the other side. So the entire table is there. You can look at for more knowledge and clarification. So here it's a normal question. I think no need of much discussion. You can look at this. The optimum moisture content is expected to be more for the test with higher energy. Optimum moisture content is more for higher energy. Is it true? No. For higher energy, you can see the graph. For higher energy, optimum moisture content is low. So the statement is wrong. First statement is wrong. Second statement, the maximum dry density is expected to be more for the test with a higher energy. Yes, for higher energy, the maximum dry density is more. So the statement 2 is correct. Out of all these options, only 2 is true. Only statement 2 is true. And of course, here again selection of the formula. It's not a big thing. And here you can look at compaction by vibratory roller. Whenever it is vibratory roller, it is always well-graded dry sand. When well-graded dry sand is used, all particles will get adjusted and density will be the maximum. Density will be the maximum. In a standard Proctor test, 1.8 kg of moist soil was filled in the mold, volume equal to 944 cc. You can see weight of the soil 1.8, volume of the mold 944 cc. A soil sample weighing 23 grams was taken from the mold and oven dried for 24 hours at a temperature of 110 degrees centigrade. Weight of the dry soil 20. So that means wet soil of 23 grams is kept in oven dried and kept in oven, and oven dried weight is 20 grams. 20 grams. Specific gravity 2.7. The theoretical maximum value of dry unit weight of the soil at that water content is. What is the question here? Theoretical maximum unit weight. Theoretical maximum unit weight. It's a routine question. You can see specific gravity is given. It is not W2. It is G 22.7. And what is theoretical maximum specific gravity? Maximum density gamma D max equal to G gamma W by 1 plus E. So for this, find out all other parameters. Bulk density gamma is Weight of the soil 1.8 kg by volume is given, so 1.907 grams per cm cube. Water content originally 23 and override 20, so you will get 15%. And basing on this S is equal to Wg by E, you can find out the void ratio. Once void ratio is known, substitute in the formula, you will get gamma D. So it's a routine question that you can answer. And of course, this is theoretical that you can look at later. So in this problem, in the previous problem, what is going to happen here is, I'll spend a minute of time for it. A clay soil has a maximum dry density of 16 kilonewton per meter cubed and optimum moisture content of 12%. That means these are the two values obtained in the laboratory. A contractor during construction of core of earth dam obtained density 15.2 and water content 11. This construction is acceptable or not? Why, if it is acceptable, why it is acceptable? That is the question. So you can look at here. So these are the laboratory values and these are the two field values. Find out the relative compaction. So field density by maximum density. So 15.2 by 16, so 95%. Already I told you anything above 90%. Normally 90 to 97%, sometimes 100% also acceptable. Since 95% is above 90%, it is acceptable. So the thing, both the dry density and water content of compacted soil are within the desirable limits. That is the answer. You can see first one, the density is less than the maximum dry density and water content is on drier side of optimum. No. The compaction density is very low. No. Because relative density is important. The compaction is done on dry side. You can done on dry side or wet side. There is no problem whether it is acceptable or not. Let us see, only 2 or 3 questions, another 5 minutes I will take, and within 5 minutes I will close the session. Compaction of an embankment is carried out 500 mm thick layers. The rammer used for compaction has a foot area 0.05 square centimeter and energy imported in every drop is 400 Newton meter. Assuming 50% more energy in each pass over the compacted area due to overlap. The number of passes required to develop compactive energy equivalent to Indian standard light compaction. Already we have seen one problem of this type. It's not so difficult. It is 604.5. For that, it will be equal to 604.5 equal to number of passes 15% more. So 1.5 into 16,000. This is the energy imported. 4,400 Newton meter divided by area. Base area is 0.05 square meter and depth of the layer is 0.5 and you will get this value. Okay, and accordingly 26 passes. Already discussed this, the same similar type of problem. And of course, in a compaction test, as compaction effort increased, the optimum moisture content decreases. That you know, like that. And here the question is unit weight of soil at 0 air voids depends on. 0 air voids depends on. This is the formula. 1 minus Na G gamma W by 1 plus E. It depends on the specific gravity. Yes. Term is there in the formula, and water content because E is in terms of W. You can see final formula when Na is equal to 0, G gamma W 1 plus W by 1 plus Wg. So it also depends on water content. It also depends on the unit weight of water. So just observe the figure formula. Whatever the parameters that are involved, so those are the variables of that particular parameter. And of course, it's also, you can look at the dry density at 100% saturation being non-linear function of void ratio. You know that the curve is not straight, it is always non-linear in nature. So with this, all the entire theory and also numerical problems in compaction of the soils is completed. Tomorrow, I'm going to deal the topic consolidation. So tomorrow I will finish the consolidation of soil, both theory, numerical problems, and also gate problems. I will complete within 2 hours or plus or minus 15 minutes. And tomorrow we will meet again. Thank you very much for patient listening, all the students. Thank you.